Hello, and the good thing about this topic is a very interesting topic. It's actually a concept that enables techniques for solving problems efficiently. So, these are the things we're going to be discussing. Then we'll look at algorithms and data structures. And from there, we'll talk about efficiency of algorithms, symptotic notation. So, but first, let's understand what an algorithm is all about. So when we say algorithm is basically a step-by-step procedure for solving a problem. Here I wrote it as set of step-by-step instructions to efficiently solve a problem. A lot of times it's not really about solving the problem that is the issue. It's about solving the problem optimally, solving the problem efficiently, and that is where algorithms and data structures come to play. So when we say step-by-step instructions to solve a specific problem, look at the word specific problem. You are solving a specific problem. So if somebody provide you a step-by-step direction on how to get to the destination, you discover that the journey will be made easy. So if I give you a step-by-step instruction in form of direction on how to get to a particular destination, I'm also giving you algorithm. Or let's bring it home a little bit. Let's say you want to cook a meal and you don't know how to cook the meal. Somebody may give you the recipe, yet you don't know how to cook it. But if somebody tells you, okay, look at how you, and this is how you are going to start. Maybe you start by slicing the vegetables, mixing some things together, give you a specific step-by-step instructions on how to cook that particular meal. Then the person has handed over to you an algorithm. And to play a game to win. That is the reason why it's programmed with an algorithm that enables the computer to win you. So the computer can be able to anticipate your move and know how to respond appropriately for every move that you make. So, and also another thing that we normally say about algorithm, everybody is talking about algorithm all the time. Maybe you on social media, people tell it means technically. So let's look at maybe Facebook, for instance. If you notice, is able to track some of the things that to give you things that are similar. Cooking channels or pages, they tend to show you more of it. That is algorithm for you. So is because as be in programming in a given language, it could be Python, it could be C++, it could be JavaScript, but what sets you as you are solving problems using computer genetic studies, maybe a step-by-step procedure on how to run the campaign that will make people to vote for a particular candidate. Or in manufacturing, that most of our manufacturing are automated. A lot of times machines are the ones doing the work. Machine will goes from here to this place, from here to there, from here to there, and then finally the finished product. That is algorithm. Whether you are playing chess or developing application for chess, or you want to make predictions in the stock market, else for you, or recommend pages you could follow. Maybe you go to some applications like Netflix, they recommend movies for you, problem to be solved. So now we're going to look at why you should learn algorithm. Number one, it makes you a professional. And like I said earlier, it is one thing to solve a problem. Another thing is solving the problem in the most efficient. Somebody gives you a step-by-step instruction on how to cook a meal. And if you follow that step-by-step instruction, you have the same meal. And if you follow that procedure, maybe you can finish cooking it in 2 hours. So if you look at the two things, you arrive at we are always very, very keen about time and space. So, but we're going to talk about time and learn a programming language without having to know about algorithms. But when you know about algorithms and data structures, you can be able to solve a problem like a professional. I remember one time when I was still learning programming, when at the early stages of my career in programming, there was an application I developed. Then the application or 20 people start logging in using the application at the same time. It start getting very, very slow. Then imagine what could happen if about 1,000 or 1 million people So I use some of the reason why you need to be very good with algorithms. And a lot of times, many companies are looking for people. Very important, or it's very crucial to design efficient or write efficient programs. So that is why you need the knowledge of algorithms. So now let's look at data structures. A lot of times people tend to mix up these two terms. Sometimes people will say algorithms, and when they say algorithms, they assume that data structures and algorithms are the same thing. They're essentially different. Data structure has to do with how you organize your data. And when we say how to organize your data, how to store, and so on. So algorithm, on the other hand, is step-by-step procedure of solving a problem. And in the instance, we'll have some data structures which you consider to be primitive data structures, like the list, that instead of a list. It's possible for you to have a list containing numbers, a tuple containing numbers, a set containing numbers. But you should be able. That is about data structures. So and like I said before, knowing which data structure to use for a given problem. And when you effectively use your data structures very well, you should be able to achieve efficiency. And a lot of times, most programmers tend to analyze algorithms, trying to know which one is the most efficient, is knowing which one will give you efficiency. So, and when we're talking about efficiency, just like the example I gave about cooking for 5 hours and cooking for 2 hours, the goal is to have an algorithm time with minimal resources. And when we're talking about resources, we're talking about memory, computer storage. There's a kind of algorithm that you will use. You end up spending a lot of your computer memory, that your computer begins to be very slow, or the application itself. How much computational time and memory, higher resources consumption, and in real life, efficient algorithms improve performance, whether it is search engine or AI models. The key is to use an efficient algorithm, which is the right algorithm for the right. And we have two ways of measuring, two approaches we use in measuring efficiency or performance of algorithms. We have the time, but our focus today is on algorithms that take the least time. And when we're talking about measuring the performance, then we'll look at this concept. We'll have growth over time. We'll have, these are some of the key concepts to keep in mind when we'll have asymptotic analysis. So let's look at growth over time. Growth over time is like, how does this algorithm perform when you have more input? For instance, if you want to count maybe 5 items and you want to count 100 items, I'm believing that it's going to take you smaller time to count 5 items than 100 items. But there's a way you can do your counting in such a way that it may take you almost the same time it takes you to count 5. So how does the function or the algorithm, slow or increase in speed as the number? That is what we mean by growth over time. Assuming you want to do a loop, maybe you want to loop and generate 1 million numbers, you may want to maybe use a time module to time before the execution started and when the execution stopped, to know how long it took for the computation to complete. This is empirical testing. Operation counting. Operation counting has to do with assuming you have a for loop looping through 5 items. For each loop, you can consider it to be one operation. So if you have 5 loops, it means 5 operation. Or another way of saying it is assuming you have a statement, a space statement whereby maybe an operation like assignment operation, or you have comparison operation or arithmetic operation. You want to add 1 plus 2. It is considered to be one operation. So when you add up all those operations, we can now call it the time, or the time, or a count of time means. And then we'll have asymptotic analysis. Asymptotic analysis also works together with the operation counting. But here we use mathematical expressions to evaluate the performance of an algorithm. So we'll look at the complexity classes before we get to the asymptotic analysis. So we have what we call a constant time function. Constant time function is a type of algorithm that executes at the same time regardless of the input size. If you say 1 plus 1, you know when we're talking about counting primitive operation, we're no longer looking at the magnitude. So when we say 1 plus 2, you are doing one operation, so it executes at the same time. It is one primitive operation. Then we have another one which we call the logarithmic, then the side. And then we'll have the limits in the proportion of the inputs perform 5 operations. If you want to count 100 items, you have to perform 100 operations. If you want to count 1 million of the input size. Then the next one is quadratic. Quadratic is normally encountered, which is also very inefficient. We also have factorial, which is also very inefficient. So let's look at the growth rates again. So like I said before, we have the logarithm time increases in the same proportion as has a combination of the linear, which is this n you are seeing here, and then this log. So this is what we call, this is also logarithmic time than the linear time. Then we'll have the quadratic, we'll have the exponential time, all. When we say factorial is multiplying a number consistently while decreasing the values. Factorial of 5 is 5 times 4 times 3 times 2 times 1. You can see how big it can get. Imagine doing factorial for 1 million. Maybe you can try it out and see the likely. Look at this growth rate. So rates are like for different times. So I'm going to show only the linear. Select, and let me deselect all these ones, so we show only the linear time. So if I do it like this, you can see that the linear time is constant regardless of the input size. And if you look at this table, you can see for linear time we have this 1 to 20. So regardless of the input size, it's still the same, which is 1. If you look at this logarithmic time, you can see how it grows. You can see that as the numbers are increasing, it is slowing down. Basically you can see from here, this is the time complexity 4. And if you look at in between this bondad 3 to 4, look at the linear with all these ones together. This is the n log, this one is the exponential time, and then apply. Remove some of them. Let me remove this log. This is slower than the linear if it were to be linear. So let me put it side by side with the linear so you can see which one is faster. So if I put it together with the linear, you can see that linear is faster than this. And let me remove this one, have the O log and the exponent together. Let's look at the two of them. You can see that n log is faster than the exponent. And let's bring this other one also. This one is, if you put the factorial, you can see how it plays. Factorial is the slowest. So this is how our functions or algorithms grow in respect to the input sizes. Then another thing again we're going to look at is asymptotic notation. This is one of the common approaches for measuring the efficiency of algorithms. And when we talk about asymptotic notations, we have the big O, which is used to determine the best case scenario. And we'll have the big theta, which is like a tight bound trying to determine the average performance, normally falls in between the big O and the big omega. So what do we mean by worst case scenario and best case scenario? So let's take an example. Let's say there are 10 numbers that are lined up together, and maybe 10 numbers lined up together, and you are asked on ordered. Maybe let me do something. Maybe you have something like this. So maybe you have a list of numbers like this. You have 2 here, you have 1 here. You want to perform a search to locate 4, for instance. What will you do? First of all, you start from here. You check whether this one is 4. It is not 4. You check whether this one is 4. You check whether this one is 4. You check whether this one is 4. And then when you get to this place, this is 4, which means you have to perform 5 operations. 8 and 3, and you are looking for 4. In this case, you start your search from here, and immediately you start the search, you find the number. So this is the worst case scenario. The worst case scenario. You cannot judge an algorithm to be efficient because of the best case scenario, which is determining the big O. So now let's look at the mathematical derivation of the big O. Imagine you have a function like this, and in this function, this is the time, and this n is the number of inputs. And this function is represented in this form: 5n raised to the power 4 plus 3n raised to the power 3. Then we'll have 2n raised to the power 2 plus 4n plus 1. And the dominant term is this 5 raised to the power 4. That is the first thing that you do. And why is this so? Because at large input sizes, this particular term grows way higher than the rest. It's just like you have 2 raised to power 5, or let's say n raised to power 2 plus 30, something like this. This 30 is insignificant. It may be significant at lower values of n, but at very large values of n, it becomes insignificant because it is constant. So imagine we have n happens to be, let's say, 100 raised to power 2 plus 30. 30 is constant. 100 raised to power 2 is going to give you what? 10,000. So you can see that this one is growing far higher than this other one. So this, with the value n raised to the power 2 plus 30, is the same thing as n raised to the power 2, or approximately equal to n raised to the power 2. And this is what we are trying. So first thing is to identify the dominant term, which is 5n raised to the power 4. Function is less than or equal to, you want to express this function in such a way that it will be less than or equal to 2 is the coefficient here, 4 is the coefficient. That's basic mathematics. The number that comes before the variable is the coefficient. So you want to represent this function in such a way that Tn, which is 5n raised to the power 4 all the way to here, is less than or equal to C. You want to get a central coefficient where you can express the function in form of maybe just using one variable. You don't have to put all these ones. So, and point, it can be from 0, it can be from 1. The number of input sizes is greater than or equal to the n0, which is the first value of the n. Maybe you can start from 0, you can start from 1. So now, for n greater than or equal to 1, look at what we did here. What we did less than or equal to. Then if you look at this function now, all of them, this one is raised to the power 4, this is raised to the power 3, all the whole powers to the power 4. That is the worst case scenario. If you want to determine the worst, so we now have, because of course this is less than 5n raised to the power 4. Remember, it's in the left side, so this is the highest that this function can ever grow to. Because we're trying to pay attention to n raised upper bound, the worst case that it can ever reach. which is this 15n. And because this function that we just derived now is less than the initial function, which is 5n raised to power 4 power 4. So now we can now bring it further and say that Tn is less than at no, which is the initial value of n being 1, we're going to get give us 15 times 1, which is 15. So if you want to represent it as big O, nobody cares about the coefficient. Just strip off the coefficient and represent it in this form. So this particular function can be represented as a big O of n raised to power 4. So this is how we came to this derivation. Then the same thing is applicable to the big omega. The big omega, we're trying to find out the best case scenario. What is the best case scenario? How can we represent this function in such a way, do you understand, that this function is less than it? Sorry, greater than it. In the case of the big O, how do we represent this function so that this function is less than our representation? That is big O. Big omega is how do we represent the function in such a way that the new, do you understand? So we'll have 5n raised to 4 over 4, which is the dominant factor. What if we say that, because this is the formula for the big omega, we want to represent the function in such a way that we have Tn is greater than, we have a central coefficient multiplied by Gn. Gn is, we no longer have 3n raised to power t, we are just using only one term here, which is n. So how do we represent it? So having determined this other one, we can assume that these other ones are 0 because they are insignificant as the numbers get bigger. So we can now say that truly it's greater, because if we start accounting for these values that we ignored, you can see that it is greater. We just remain and you remove the percentage, the decimals. Do you understand? So let's consider this to be the decimals, which we removed for approximation's sake. So that is how we came about with this. This function is greater than 5n raised to power 4. So now the coefficient becomes c, and then the no becomes 1. Represent it explicitly, then you have to indicate 5n raised to power 4. Then we'll look at the big theta. Big theta has to do with determining the tight bound. You're trying to find a function in between the upper bound and the lower. That is anywhere in between the lower bound and the upper bound. So this is the lower bound and this is the limit to n raised to power 4. So this is how we'll do the derivations for the big theta. But a lot of times in your algorithm analysis, your emphasis should always be on the big O. So this is where we're going to be ending this class on Introduction to Data Structures and Algorithms. On Friday, we're going to do another live YouTube where we're going to start learning about the different algorithms, like the recursive algorithms, search algorithms, and so on. We'll look at other data structures like linked list and so on. We're going to be treating it one after the other. So this is essentially an introduction to data structures and algorithms with emphasis on analyzing